Welcome back, everyone. We are continuing Unit 2. This lesson will focus on periodic table trends. The periodic table trends that we will discuss are atomic radius, electronegativity, and ionization energy. Now, just trends refer to how something changes, so the pattern. Atomic radius is half the distance between the nuclei of two atoms of the same element that are bonded together. So here we have a picture of two atoms being bonded together. The distance between the nuclei, we're going to label it as d. Half that distance is what the atomic radius is. So we can say d divided by 2 is equal to the atomic radius. Now, as you move across a period, the atomic radius is decreasing. A little bit of review. Period meaning left to right on the periodic table. So across a period, the nucleus of the atom is gaining more protons, and the valence shell is gaining more electrons, making each of these charges stronger. Now, across a period, the number of shells remain the same. Remember that the period number indicates the number of orbitals the element has in that period. So, if we're talking about the shells remaining the same, across a period, the positive charge in the nucleus is growing stronger, and now it's attracting or pulling the electrons closer to the nucleus. And so this shrinks the atom's size, and that's why the atomic radius is being decreased across a period. Now, down a group, the atomic radius is increasing, and the reason for that is because the number of energy shells are increasing. So here, if we start from the top, the elements in period 1 have 1 orbital. The elements in period 2 have 2 orbitals. The elements in period 3 have 3 orbitals, etc. So now it's becoming bigger and bigger because now we have more shells. You can think of it as layers. Now there's more layers to the atom, so it's becoming bigger. Electronegativity refers to the ability of an atom to attract electrons when the atom is in a compound. When you see the word electronegativity, you should think of love for electrons, because we're talking about attraction to electrons. Now, electronegativity is measured using a relative scale. It is not measured in energy units. What do we mean by a relative scale? All the elements on the periodic table are being compared to one another, and we have an element that is the most electronegative element. And that element, it is fluorine. Now, fluorine has an electronegativity of 4.0, the highest electronegativity value we have on the periodic table. As you move across a period, the electronegativity increases. The reason for this is because all the atoms want 8 valence electrons. So the closer an atom is to having 8 valence electrons, the stronger it's going to hold on to its electrons. So let's take an example, let's say fluorine. Fluorine, we said, is the most electronegative atom. Electronegative is talking about the attraction to its electrons. So fluorine has 7 valence electrons. Now, fluorine is very close to having 8 valence electrons. It's actually only one step away from having 8 valence electrons. So it wants 8 valence electrons. It's very close, so it's holding on to its 7 valence electrons very strongly. Electronegativity as you go down a group is decreasing, and the reason for that is because there are more and more energy levels being added to an atom. Thus, the distance between the nucleus and the valence electrons is growing. Ionization energy. that refers to the energy required to remove an electron from an atom. It is measured by kilojoules per mole. So here we have an image of one atom that has a high ionization energy and another atom that has a low ionization energy. Let's take a look at the left. This atom has 1, 2, 3, 4, 5, 6, 7. So we can say that this atom represents fluorine. It has a high ionization energy. And the caption reads, "Mine, mine, all mine, don't touch. No touchy." And the reason for that is because it's so close to having 8 valence electrons. It's one step away. So it doesn't want to let go of its electrons because it's one step away from where it wants to be. Now, this atom on the right-hand side has a low ionization energy. And the reason for that is because it's very far away from having 8 valence electrons. It only has two valence electrons. So in this caption we read, "Sure, whatever, take them." The atom is far from having 8 valence electrons, so it really doesn't mind if it loses 1 electron. So this atom here has a low ionization energy. As you move across a period, the ionization energy is increasing. And the reason for that is because it's getting closer to having 8 valence electrons. The closer an atom is to having a full valence shell, the harder it's going to be to take away an electron. So the harder it is to remove the electron, the more energy that is going to be required. So here we can refer once again to fluorine being one step away from having 8 valence electrons like neon. And here we have a picture of king neon. The elements that we see in group 18, they are called noble gases. And the reason that they are called noble gases is because they have 8 valence electrons. Everybody else that doesn't have 8 valence electrons wants to be like them. So that's why they are referred to noble gases. All right, so going back to ionization energy, it increases because fluorine is one step away from being like royalty, which is right here, king neon. So it's one step away from being like royalty. It's going to give a very tough time for anything that is trying to take away its electron. That's why ionization energy is increasing across a period. Now, ionization down a group, that is decreasing. And the reason for that is because down a group, the energy levels are increasing. So there's more and more orbitals as you go from top to bottom on the periodic table. This makes that the electrons are now further away from the nucleus. And since the distance between the nucleus and the electrons are increasing, there is a weaker attraction or pull between the positive and negative charges. We can refer to this as electron shielding, when the inner electrons shield the valence electrons from the full attraction to the nucleus. Now, if this is happening, the valence electrons require less energy to remove. You can think of this as like a magnet holding on to paper on a fridge. The more pages you add, the weaker the attraction between the magnet and the fridge. And now it's easier to remove the pieces of paper. Now here we have a summary of the periodic table trends we have discussed and how they change across a period and down a group.